Next up is the electric potential. We talked about electric potential and electric potential energy in the last unit, but this part of this unit actually shows us where the formulas come from, and we're going to use some calculus that makes your head hurt yet again. But hopefully you'll find this a little bit easier than our ones we started with last unit. But here we go. Electric potential energy. We've talked about this electric potential energy before. When electrostatic force acts between two or more charged particles, there's going to be some energy between them. We know this. If we have two positive charges, we can make them come together. We're going to do work on them, and once we've done that work, they're going to have some potential energy between them. Because those positive charges are going to want to repel, that potential energy will be converted to kinetic energy. If the system changes from initial to a final state, then work is done on that particle. And so my change in internal energy is from my final to my initial state, and that's going to be my negative work. The negative work has to do with the direction of that occurring, because if we bring these closer together, they're going to have some potential energy between them, and the work is going to be in that opposite direction. For potential energy problems, most of us will start off at infinity, because remember, we have to have a reference point. Whenever we have energy, when we have gravitational potential energy, the reference point's usually the ground. When we're talking in terms of electricity, we're going to move something from infinity to point P. And so when we move from infinity, that is done so, one of our reference point, our point of the initial point, will be 0, because an object infinitely far away will have 0 potential energy. And so that's what this part right here says. If we move it from infinity, far, far away, it will be 0 to our final state. And so the potential energy at our final state will equal our negative work as we move an object from infinity to that point. If you remember from your internet homework from last unit, there were some questions and y'all always got confused about what's it talking about moving from infinity. Well, this is why. It's so that our formulas work out, because we have to have a comparison between 2 points. A proton moves from point I to point F in a uniform electric field directed as shown. Does the electric field do positive or negative work on the proton? And then does the electric potential increase or decrease? And so if we look at this, our electric field is pointing to the right. Remember, our electric field always points from the positive to the negative. So if I bring a positively charged particle and I'm moving it from I to F, this thing is moving towards the positive particle. Does it want to do this? Heck no. Do we have to impart work on it? Yes, we do. And so our work here will be positive. So on the next part, does the electric potential energy of the proton increase or decrease? So if it was over here at this point right here, we are so far distance away. As I move closer, I'm doing work on it, and it's closer, so the electric potential energy has then increased. Hopefully you can see that. Closer it is, it's going to have more potential energy to that positive charge. So here's this thing that everybody gets confused on, this electric potential. What the heck does it mean? What is it? What is it? What is it? What is it? And so basically it's just something that we can measure that gives us an idea how much energy each unit charge has within an electric field. And so we talked about this before. The electric potential is the potential energy that a test charge experiences. This electric potential is a scalar quantity. The only measuring device that we have measures the change in potential, the potential from our final to our initial position. And so if we put the little triangles in here, we get delta V equals delta U over Q. And we just learned that delta U is the negative work, and so my potential is going to equal to, or my change in potential is going to equal to the negative work over Q. If we set our initial energy to 0 at infinity as our reference point, then the electric potential at energy point becomes the negative work as we move from infinity per unit charge. This is known as a joule per coulomb, known as the volt. In the lab you did, you should have seen these equipotential surfaces. These are adjacent points that have the same electric potential from an equipotential surface. Here is the important part. No work is done on the charged particle when it moves between the same equipotential surface. And so if my red line here is my equipotential surface, if I move from point A to point B, I have not changed my potential. My delta V is 0, therefore the work is 0. However, if I move from point A to point C, I am changing my potential, so I will have done either positive or negative work depending upon what those lines are. In a circular format, it's going to be the same thing. These red dashed lines are our equipotential lines. The blue lines are electric field lines, and with point charges we saw that. Hopefully on the lab you were able to visualize these equipotential lines as you tested it with the voltmeter. Many times we need to calculate that electric potential from the electric field. And so what you need to remember is a couple of things. Remember that work is going to equal to force times distance. And so if we are doing a bunch of little bitty paths here, we're going to break into little bitty components. That's where that dW comes from. We're going to have the force times the little bitty dx. What type of force are we talking about? We're talking about the electric force, and hopefully you remember that the electric field is the force that a test charge experiences, so this force is going to equal to EQ. And so we get dW equals EQ dx. We can integrate both sides and pull out that constant, and we get work as being the integral of E, pull out the Q, dx, as we go from our initial to our final state. Now, if you don't like the derivation of this formula, you can remember that work is the integral of f dx. Hopefully you remember that. And what type of force are we talking about? We're talking about the electric force. So we have this EQ times this dx. The q comes out because it's a constant, and so we get work as being the integral of E dot dx from our initial to our final state. Now, remember up here a minute ago we talked about what work is equal to. Hopefully you remember that work is going to equal to, let's go right back up here where we saw it. Work is going to equal to this delta VQ. So if I have the negative work equals the change in volts over Q, I can plug this into this formula. So this work, negative, I'm going to do it this way, V times Q is going to equal to Q from our initial to our final state, E dx. These Q's are going to cancel, and I can move this sign over, and so I get the change in potential equals negative E dot dx from our initial to our final state. There will be times that you will have to apply this integral, and this is the format that will enable you to do so, and you'll see that as we work some free response problems. Again, if we move from infinity to a certain point, our initial velocity will be, initial voltage will be at infinity, and so that value will be 0. And so we're equal to our potential is the negative integral E dot dx. The figure shows a family of parallel equipotential surfaces and 5 paths along which an electron from one surface to the other. What is the direction of the electric field associated with the surface? For each of the paths, is the work positive, negative, or 0? And rank the paths according to the work done. Alright, so first of all, what is the direction of that electric field? Remember that the electric field has to be perpendicular to our equipotential line. So first of all, we have to know that it's going to be either going to the right or to the left, because it has to be perpendicular to that way. And as we go down, we should see that lines are always drawn from the positive to the negative, and so that gives us a rightward direction for our electric field. Okay, now here comes the hard part. For each path, is the work positive, negative, or zero? You're going to get confused with the signs. I'm going to get confused with the signs, so walk me through this, make sure I see this. So in path 1, my initial state is 80. My final state is 70 volts. And so my change in volts, which is going to be 70 minus 80, is going to equal to the, let's go back up here. What is it equal to? The negative work per unit charge. Negative work per unit charge. Negative 10 equals negative work over charge. Negative times a negative is a positive. So part A, that is positive work. Part B, I'm sorry, that's path number 1. Path number 2, 80 to 70 again. This is going to be the exact same value to before because we don't care about the path. We just care about our initial and our final states. State number 3, my initial voltage is 80 volts. My final ends up being here at 60. Final minus initial. So again, that's going to be a negative 20 over negative work over charge. Again, negative and a negative. This one's going to be positive. On number 4, I start right here at 60 and I go to 70. So my initial is 60. My final is 70. So I'll have 70 minus 60 equals a negative work. And so my work here is going to be negative. And then the 5th one, start at 70. My final is 60. So I'll have 60. I don't know why I wrote BI. 60 minus 70 equals the negative work. So again, I'll have this negative 10 equals the negative. So negative and negative, that ends up being positive. Rank the paths according to this. And so as we look through here, which one is going to have the greatest amount of work per unit charge? And as we do this, hopefully you can see that the one that is the most is this one that has this 20. So number 3 is going to be the highest. And then we have 1 being 10. 2 is the same thing. It's 10. 4 is 10, but it's negative work, so it's going to be at the end, and then the last one. So we're followed by 3, then 1, 2, and 5. These guys are all equal. And then the last one is 4. So that is our correct ranking on that part of that. Okay, what we're going to do here is show the calculus derivation of our formula that we learned for potential, which is KQ over R. And so what we are seeing this is we're going to have some positively charged particle that's at infinity, and we're going to move it here to point P. And we want to calculate that electric potential, the electric potential, as we move it from infinity to point P. And so our formula ends up being the change in volts, and that's a V, that's a really ugly V, but here it is, equals the negative integral E dx as I go from infinity to state R. And let me make sure that, well, let me go this way. Let's go from our initial to our final states. And so that's going to flip that, which I'm going to have to think about why that happens, but we'll make it work in just a second. Oh, because the way this one's written. Okay, this one's written as going from point P over where to infinity, so I'll switch it that way so it makes sense to you. So we're going to take how much potential does an object have if we move it from point P off to infinity. So we'll have our final minus initial states, and we're going from a final state to infinity to R equals E dot dx. So as we look at this, we know at infinity that term's going to go away, so there will be R0. The electric field. We should remember that the electric field is going to equal to KQ over R squared. And so we'll end up, and I'm just going to rewrite this because I don't know why. KQ from R to that over 1 over R squared dx. And so now we get to do some calculus with this. And so as we do that, what will happen is that we will get our formula that we know and love. And so as we do that, we will get a value of, well, I don't know why they're doing it. We're going to make this into dr. I'm looking at this book that I got this from, and it's not making a lot of sense to me, so we're just going to do that. As we integrate r to the negative 2 dr, add 1 to the exponent, so that's going to be negative 1 over r, or actually r to the negative 1. And so we end up with a negative kq times a negative 1 over r, going from r to infinity, and we plug that in, we get the potential to be the formula we know and love, kq over r. And so again, that is the calculus derivation of this. If you get it to this point right here, stick it into your calculator, let your calculator integrate it for you. And so that's how it derives that. Unfortunately, very seldom do we have a single point charge. We're going to have a single continuation, lots of charges. And when we do so, we just take the algebraic sum, not the vector sum, of the individual potentials. All we have to do is add them all up. And so if we have this dv term, it's just the dq over r, and we integrate accordingly. Let's look at this line of charge and see if we can figure out how to do this. Again, you're going to think this is hard because it looks hard, and it's because we did this at the beginning of the first part of the notes, and y'all were having troubles with that. Maybe this will make a little bit more sense. What we want to do is calculate the electric potential at point P due to this continuous line of charge. Here's my line of charge right here. And so what we need to do is we need to add up all these little bitty slices, and we're going to go from 0 to the length of the rod, and we're going to see how these affect at point P. So in order to calculate this r distance, it's going to be this Pythagorean theorem, which is going to be x squared plus d squared square rooted. And hopefully you see I'm going to have these little bitty slices. That will be some dx. If it has a uniform charge density, remember that's charge per unit length, so that's going to equal to dq over dx. dx is that length of that little bitty slices. And if I'm looking for my potential, I end up with integral dq over r, which is kq over r, which we know how to do that. And so to get rid of my dq here is going to be lambda dx. And what is my r distance going to be? It's going to be this distance here from point P to my rod. And so I'll get k times the integral of lambda dx over x squared plus d squared square rooted, going from 0 to L. I'm going to pull out the lambda because it is a constant, and so I'll have to integrate this dx over x squared plus d squared right here. Now, at this point, this is the point that I am going to let my calculator do this. So I pull out my calculator here, and I want to do some calculus, so I'll hit number 4, and we're going to do an integral. We're going to integrate from this from 0 to L. Where's the L? And I'm going to plug in my fraction, which is going to be 1 over x squared. You would think I'd know where these x's are, but I don't. X squared plus d squared. And that is raised to the 0.5 power, and I'm integrating this with respect to x. And so when I do so, I get that value right there. That is what they want to see. And once you have that, you are done with this problem. You will write this down as you see it, because that is what they want to see. So that potential is going to equal to, remember this k lambda we pulled out, times L squared plus D squared, square rooted, plus L over D. And hopefully you didn't find that one too terribly bad. In addition to having these little lines of charges, we might also have a charged disk. We'll have a charged disk of uniformly charged density lambda. And so again, lambda is charge per unit area. And here comes the area. How can we do this area? If I take this little red slice and I break it apart, hopefully you can see that this is going to be the circumference 2 pi r times my dr. And what's going to happen is I'm going to take all of these little bitty slices and I'm going to add them all up. And so we'll integrate from 0 to a capital R, which is the radius, and we'll just keep adding all these little bitty slices here as we go this. And so my area here is going to be 2 pi r dr. And so our potential is the integral of k dq over r. And as I look at this, my dq is going to be lambda 2 pi r dr. And what is going to be the x distance? Hopefully you see as I take these little bitty paths here, this is going to be r squared plus z squared square rooted. And so I'll use that for my radius as we go along here. And so as I fill out this integral, I get lambda 2 pi r dr over r squared plus z squared to the 1/2 power. Pulling out those constants, which is lambda and 2 pi, gives me k sigma 2 pi integrate r dr over r squared plus z squared to the 1/2 power, and I'll integrate that from 0 to capital R. I'm going to change that when I put in my calculator because the calculator is not going to recognize little r and capital R. So when I'm playing the calculator, I'm going to use L. Don't freak out when you see that, but that is what we're doing on that one. And so when I pull it over to my calculator here, again, we're going to integrate this. And so I will go back to my menu. We will do some calculus, and we're going to integrate that. And again, 0 to L, which L is just the radius there, just running out of R's and it won't recognize it. So that's what I'm doing there. Need this fraction here, so I'll put in a little fraction. And I'm going to have an R on top. And R squared plus Z squared. And get my raised to the 0.5 power, and that is going to be with respect to R. There you go. And so that gives my value right there. Remember, this L needs to be an R, and that's it. You're going to leave that alone, let your calculator do the calculus for you. And so your final answer is z squared plus r squared. That's a z. Why did I write an x? Because I don't know. Minus z here. And that is the final answer for that electric potential. Again, am I expecting you to do this? No. Is it probably in your calculator? Probably. Do you need to understand this and start being able to apply this? Hopefully yes, especially those of you that want to get 5s on this. Alright, can we go the other way? Can we calculate the field from the potential? The answer, of course, is yes. Suppose that a positive chest charge moves through a displacement dx from one equipotential to another surface. So how do we do that? Well, we know that work is going to equal to the negative potential energy. And hopefully you know that the potential energy here now is negative Q times the change in volts. And since we're talking calculus, I'll get rid of the delta and make it dV here. Well, what is work equal to? You know that work equals force times distance, and we're going to move it some dx here. And so what type of force are we talking about? We're talking about the electric force. So EQ dx equals negative Q dV. And so the Q's cancel, and if we solve this, we get the electric field equals negative V dx. What does this mean? If you are given a electric field, and you want to, if you want to calculate the electric field, you're going to take the derivative of the potential function as a function of x. So if they give you the volts as a function of x equals 4x squared plus 3x, and you want to calculate the electric field from that, this is what you do. You're going to take the negative derivative. So 8x plus 3. Don't forget that negative sign because it has to be here. So the electric field, negative dV dx. And then remember that potential is the negative E dot dx. So again, make sure you know, are you trying to calculate potential or are you trying to calculate the electric field? Okay, here we go. This is where you're going to see this in terms of the Gauss's law inside those charged conductors. So pay attention. This part is important as we go here. We talked about a conductor before. We know, where does all the charge hang out on the conductor? Hopefully you know it's hanging out on the surface of that conductor. And if it hangs out on the surface of that conductor, the electric field inside of a conductor, by definition, is always zero. So the electric field is zero for all points on a conductor. We know the excess charge lies on its surface and the electric field is perpendicular to that surface. So if the excess electric charge on an isolated conductor will distribute itself on the surface of the conductor, here's the important part, so that all parts inside the conductor come from the same potential. This is true even if the conductor has internal cavity and even if the cavity has net charge. Where does this come from? If this electric field is zero inside of a conductor, what does this have to be? Well, hopefully you can see that the change in V has to equal to zero. So if the change in V is zero, then VF equals VI, and so all points within the conductor are going to be at the same potential. So this is the graph. They are loving graphs. You need to make sure you understand this. So if I plot from 0 to some radius here from inside of a conductor, and this is only true for a conductor, notice that from here to the surface, and my surface, this R is going to equal to 1, I'm going to be at the same potential here. As I get out of this, it now turns into my good old formula, which you know is KQ over R. So notice that this curve is on the basis of R. Our electric field, though, if we plot the electric field as a function of R, you should know that the electric field inside of a conductor is zero. Once we reach that surface, the electric field is going to be in a maximum, and this electric field is proportional to KQ over R squared. You're going to work some free response problems doing that, and this is very important. If you know nothing else, make sure you remember these two things and then our formulas, that the change in volts is the integral of negative E dot dx, and then the electric field is the negative derivative of potential as a function of x. Big three right there. Hope it made sense to you.